Let's turn our attention now to the topic of graphing a derivative function based on the graph of an original function. In other words, if we have a function and it's graphed, we want to look at the graph of the original function and predict the overall shape of the graph of the derivative function based on the graph of the original. Now remember that the derivative is a rate of change. It is the change in the y with respect to the change in the x, dy dx. It can also be considered to be the slope of the tangent line. And we will be using this idea of the slope of the tangent line to predict the overall shape of the graph of the derivative based on an original graph. Let's now turn our attention to our first example, which is the square root of x and its derivative function 1 over 2 the square root of x. So when we look at the graph of the square root of x, remember it's sort of like an upper arm, like someone maybe, I don't know, doing the American crawl when they're swimming. So this is sort of like an upper arm coming up. It is in fact the upper arm of a right opening parabola, but only the upper arm. So you can see it pictured here in dark blue. Now, when we look at this function, we want to analyze the function based on whether the function is increasing or decreasing, whether it has a positive slope of the tangent line or negative, whether it has maximum places and minimum places. These are the kinds of things we're looking for, whether it changes the way that it's curved. So when we're looking at this particular one, notice first of all that it is increasing over the entire domain of the function square root of x. That is that the y values are going up in value as the x values increase. That means that the slope of the tangent line is always positive. If you hold your hand straight, like it's the tangent line on the curve, you'll see that your hand always has an upward tilt as you move along the curve. That means the slope of the tangent line is positive. Now, when we talk about the curvature of it, we're talking about whether it is curved down, sort of like this, down like a frown, or whether it's curved up like a cup, sort of like this. So we can think of down like a frown or up like a cup. We call this the curvature or the concavity of the curve. When it is up, we consider it to be positive curvature or positive concavity. And when it is down, we consider it to be negative curvature or negative concavity. We also want to look to see if there are places on the original graph where we have high points or low points on the graph, relative maximums and relative minimums. This particular graph has no relative maximum and no relative minimum. And in fact, there's no place that's higher than all the others. And I suppose you could say there's a place that's lower than all the others, but that's really the beginning of it. All right. So we don't really have a place where we have a valley in the curve where it comes down to a dip, or a place where there's the top of a hill in a curve. That's what I mean by a maximum or a minimum, lower than the points near to it on the left and the right, or for a maximum, higher than the points near to it on the left and the right. This particular graph also does not have a change in curvature. Notice that it is more or less cupped downwards over its entire domain. So it never looks like it's cupped upwards. It's always curved this way. We call this concave down for concavity. So it's always concave down. Now, what we want to do is we want to analyze the graph, and we're going to start with increasing and decreasing behavior. Then we look at maxes and mins, and then we can look at the curvature or the concavity. These are the primary three things we're looking for: increasing, decreasing behavior, places where we have relative maximums and relative minimums, and changes in the curvature. Now let's start on the left side of the graph, put our hand on the graph as if it were the tangent line, and start talking about what the graph is doing. It's increasing from the left to the right, the way we read a graph. Yes, it's left to right. There is a way. Then we go up, and notice that the tangent line is becoming flatter as we move to the right along the curve. It never becomes flat. It doesn't go horizontal. It stays at an upward tilt, which means that the slope of the tangent line is always positive, but it is getting flatter the further out we move to the right. So it is decreasing in value because the slope is becoming smaller, but it stays positive. This means that we expect the derivative to start with a high value where it's very steep, and then to gradually come down, and then to very, very slowly start getting flatter and flatter and flatter. It never goes horizontal, but it may get close to that. So we can see here on the graph of the derivative, which is pictured in this orange-red color, that it starts out with a positive value, very high, which means it is far from the x-axis. And then it gradually decreases, the slope of the tangent line does. And as it gets close to 1, we can see it really has done this major change from very steep here near the origin to much flatter here near x equal 1. And we can see this change here in the graph of the derivative as it comes down from close to x equals 0 to near 1. From 1 out to the right, the slope of the tangent line becomes flatter, but it never goes 0. It's slowly, slowly decreasing. And we can see in the graph of the derivative that it is slowly, slowly decreasing, but staying positive. Positive meaning above the x-axis. Now we have no relative maximum and we have no relative minimum, and the curvature stays more or less cupped down over the entire graph. And so we don't have a change in concavity either. These would correspond to different types of behavior on the graph of the derivative. So what we want to look at now is we want to look at another curve that has a different type of thing happening. This curve is x squared minus 2x. When we look at the graph of x squared minus 2x, which is pictured here in the dark blue, we get a parabola. In fact, we get an upward opening parabola that has 2 x-intercepts and a vertex down here at x equal 1. When we're looking at this particular graph that is a parabola opening up, we want to predict what does the graph of the derivative look like based on this graph. Now, this graph has something that the last graph did not have. It does have a place of relative minimum on the graph. Right here at the vertex, it is lower than all the points to the left and to the right. It's lower on this interval than all other points. That makes it a relative minimum. In fact, it's lower than all the points on the graph, period, which makes it an absolute minimum. But what we really care about are even just relative ones, higher or lower than all the points nearby. So this is going to produce something different in the graph of our derivative. But again, we're going to start on the left side and move to the right side. We first look at increasing and decreasing behavior. If it's increasing, the slope of the tangent line is positive, and that means it should be above the x-axis. If it is a decreasing function, then the slope of the tangent line will be negative, and the value of the derivative should be below the x-axis. After that, we'll look for places where we have relative maximums and relative minimums. These places correspond to points where the value of the slope of the tangent line is 0. In other words, right here at this relative minimum, the tangent line goes horizontal. The slope of a horizontal line is 0, which means that places of relative minimums and maximums correspond to x-intercepts on the graph of the derivative. The third thing we would look for is a change in the curvature. And again, the curvature is either concave down or concave up. In this particular case, the entire graph, the entire parabola is concave up. It never changes curvature. A change in curvature would be a place where it changed from being cupped down to being cupped up, or vice versa. You would see a change in the direction of the curve. There's no change here. So we won't see the third type of effect on our graph of the derivative. But let's examine it again, starting at the left, looking at increasing, decreasing first, as we did in the first graph, the square root of x, and then we'll look at the effect that this relative minimum has on the graph of the derivative. As I examine the graph from the far left to the far right, the first thing I notice is that it is decreasing over the interval from negative infinity up to 1. Because it is decreasing, if I put my hand on the graph to act as the tangent line, then I notice that it is relatively steep, but negative. So the slope is relatively large in absolute value, like a 4 or a 5, but it is negatively sloped downhill. Again, read your graphs from the left side to the right side. That is downhill. This would be uphill. So it is negatively sloped all the way as it is approaching the vertex of the parabola. But as it gets closer to the vertex, notice that it becomes less steeply sloped. It's gradually flattening out until it reaches the vertex. At the vertex, it goes to 0. What is this going to mean in the graph of the derivative? Well, because it has a negative slope, I expect the values to be below the x-axis. And you can see here that they are. At this point, this is about a slope of a -4 or a -5. And corresponding to this point underneath, you'll see that on the graph of the derivative, the value is about -4. Then as it moves closer to the vertex, the slope of the tangent line gradually becomes less negative. It actually means it's increasing because -4 to -2 is actually an increase in value the further to the right you go. So it is becoming flatter. That means the value about here is about -2 when x is 0. As it approaches the vertex, it goes to 0. So it comes up in a linear fashion and has an x-intercept directly above that point of relative minimum. A point of relative minimum or relative maximum will always correspond to an x-intercept on the graph of the derivative. Now let's keep going and let's look at what happens from the vertex to the right. As we move from the vertex to the far right on the domain, from 1 to infinity, it begins to increase in value. That means the y values are going up as the x values increase to the right. Notice that it starts out flat at the relative minimum and then tilts ever so slightly uphill. Then it tilts a little more uphill, then more uphill, then more uphill. It's becoming steeper as it moves to the right. Because it's becoming steeper, the slope of the tangent line is getting larger in absolute value. That means that it starts out a little bit positively sloped, and then the slope becomes steeper and steeper. It turns out that when you look at the graph of a parabolic shape, the graph of the derivative is about 1 degree less, which means it's linear. So a parabolic shape has a more or less linear derivative. And in fact, that's always going to be the case. Now, on some shapes, it won't be a perfect parabola, but again, it will be more or less linear for the graph of the derivative if it has a more or less parabolic shape in that region. Now we want to take a look at actually practicing the skills we've gained so far, interpreting increasing and decreasing in terms of positive and negative slopes of the tangent line, interpreting relative maximums and minimums as x-intercepts on the graph of the derivative. There are 2 different applets that I like to use to help practice the skill of drawing the graph of the derivative based on the graph of the original. They're both actually GeoGebra applications, and they're essentially identical. So you can use either one. Let's take a look at the first one. When you get to the applet, what you're going to see is the graph of the original function in black on the screen. When you look at this, the original function is black. Now, the next curve is this one here in blue with all the dots on it. This is the one you're going to manipulate to try to get it to look like this equation or the graph of the derivative function. So the original function is black, and we're going to manipulate the blue until we think it looks like the graph of the derivative. Then we'll be able to check our accuracy to see how accurate we are. Now, I do warn you, normally, if I get a 70% accuracy, I am celebrating, woohoo, because that probably means I've got the general shape right. I'm just not going high enough or low enough, or I'm going too high or too low, but I have the general shape right. So if you can get to 70% accuracy, that is probably what your professor is looking for. So again, it doesn't have to be 100%, and it probably won't be 100%. And then when we show results, we'll be able to put the true derivative on there, and we can compare our estimated graph of the derivative with the true graph of the derivative. Let's get started. We're going to take a look at the one that's up here now. This one has the third type of change that we need to learn about in order to draw the graph of the derivative from the original. It has a change in curvature. So we can see that it is increasing as we proceed from the far left at negative infinity, increasing until it reaches about 2. At x equal 2, it begins to decrease and comes down like this. Where it is increasing, the graph of the derivative should be positive. And where it is decreasing, the graph of the derivative should be negative. Positive means above the x-axis, and negative means below the x-axis. So we can already go ahead and change some of these values. Since we know when it's increasing, these should all be somewhere here above the axis. And when we get past 2, these should be somewhere below the axis. Now we're just using our knowledge of increasing and decreasing to decide the sign of the slope of the tangent line. Again, put your hand on the graph as the tangent line. It is slightly uphill, which means it's relatively flat. Relatively flat means close to the x-axis. So we're going to take this point, which is up here and further away, and we're going to move it to still be positive, but relatively close. Now the next point over, what's happening? Well, what's happening is that it's becoming more steeply sloped. As it becomes more steeply sloped, that means the slope of the tangent line is going up. So we know that this one should probably be higher than this one, and that should probably continue for a little bit. But we have a change in curvature, and this is new for us. This change in curvature is going to affect whether the slope of the tangent line is still increasing or whether it begins to decrease. And what do I mean by the change in curvature? Look at this first part here between -6 and about -1. It looks like it's cupped up. It looks like it would hold water. So if it holds water, then it must be concave up. However, clearly somewhere in here between -2 and 0, it changes curvature because it's clearly concave down between 0 and 5. It's clearly cupped down. The water would tip out. It would not hold water. That's concave down. When we have a change in concavity, it means that we have a change in the behavior of the slope of the tangent line. If it was increasing at the change in concavity, it will start decreasing. If it was decreasing at the change in concavity, it will start increasing. So in other words, the point where it changes concavity becomes a relative maximum or a relative minimum on the graph of the derivative. I think, based on looking at the graph, that the change in concavity occurs about at -1. That means that until I get to -1, the slopes of the tangent line are increasing and going up in value. So when I come to the dots, I want these values to be increasing and going up in value until I get to about -1. When I reach -1, then I have a relative maximum on the derivative. At -1, it's going to stop increasing because when I get up here to this relative maximum, the slope of the tangent line is 0, which means it's got to stop increasing and start decreasing. And that change occurs at the change in concavity. That point is called an inflection point. An inflection point is where a curve goes from concave up to concave down, or vice versa. In our case, from concave up to concave down. So where it changes, it stops becoming more positive and starts flattening out again, which means the derivative stops going uphill and starts going downhill. We know that when we reach a relative maximum or a relative minimum, we should have an x-intercept on the graph of the derivative. So directly below 2, where I think that is occurring, I'm going to put an x-intercept. And in between, I think that basically it is increasing in value until it reaches the inflection point, the change in concavity, and then it starts to decrease and go back flatter again until it reaches the point of relative maximum. At the point of relative maximum, what happens? As I continue to move over, it tilts just a little bit and becomes slightly negative. Slightly negative is a small negative value, so it's close to the x-axis, but below it. Then it becomes more negative, more steeply sloped as we move to the right, which means that these values should be all negative and increasing in absolute value, which means decreasing in true value. I'm going to take these dots and I'm going to rearrange them so that it becomes slightly negative, then more negative, then more negative, then even more negative. So it looks something like that. Now, do I know that the graph of the derivative looks exactly like this? No, I don't. I hope it has the general shape though. So let's try it and see. Who knows? Let's check our accuracy. When we click on check accuracy, I get 73%. That is my normal about range, somewhere in the 70% range. Anything that's 55 to 75 is probably pretty close. Anything that's below 55, you've probably missed a piece of the graph. If you get above 75, you're doing awesome. Now let's put the true graph of the derivative on here and check to see whether our basic shape, increasing and then decreasing and crossing somewhere near 2, let's see if that is relatively accurate to the true shape of the derivative. We click on show results and it says, not bad. And it's not bad. You can tell that the derivative is increasing, but not as much as what I had it increasing. This point is definitely should be lower. And then it comes down more gradually than what I had it doing. And it does hit the x-axis very near to 2. And then the value starts going down. Now notice this behavior right here. I missed something in the graph of the derivative. Notice how this is decreasing and then starts to increase again. There must be another change in curvature right in this section of the original function. Why? Because there is a relative minimum on the graph of the derivative. A relative minimum or maximum on the graph of the derivative is an inflection point on the graph of the original, a change in concavity. Why did I miss it? Well, there's just really not enough of the graph here to predict that it changed and to see that change in curvature. Sometimes changes in curvature are subtle and we don't always catch them. Let's try it again. If we want to try it again, we can click on reset the graph and we can look at another one. Now this one has both a relative minimum and a relative maximum. And I can tell from the shape of the graph here towards the bottom on the far right that there is again another change in curvature, because I can see here that this section is cupped up like a cup. So I know it's cupped down here, and the last little bit looks like it's turning and coming back up again. So the curvature is up. So I have an inflection point somewhere in this region. I also must have an inflection point in this region because it was cupped up and now it's cupped down. Because I have a relative minimum, I've got to have an x-intercept about here. And because I have a relative maximum, I've got to have an x-intercept about here. Let's use increasing and decreasing to predict where it is going to be above the x-axis and where it's going to be below. And then we can also use our predicted locations of the x-intercepts to help us draw it. From the left, proceeding towards the right, the way we read graphs, it is decreasing over the interval from the far left until about, well, let's say about negative 3.5. When I get to about negative 3.5, it looks like it is changing a little bit. All right, so we think there should be an x-intercept somewhere in here around negative 3.5. Now, if the graph is decreasing here, that means the slope of the tangent line is negative, which means it should start below the axis. It is steeper here than it is here, so it must be further away from the axis and getting closer to the axis as we approach this relative minimum. So I'm going to drag the point where x is negative 6 below the x-axis, and I think it's about a negative 3. And then it's going to come uphill, and it's going to get closer and closer to the x-axis as it becomes flatter and flatter. Now, I think somewhere in here is where it should cross. And notice again that this section of it is kind of linear because this part of the graph is kind of parabolic. And that's the way that the graph of the derivative relates to the graph of the original function. Now, I know that somewhere in here, I've got an inflection point. Remember, the inflection point will be a relative maximum or a relative minimum on the derivative function, a high or a low point on the derivative. As I move to the right from negative 3.5, it was flat, and then it tilts ever so slightly uphill, and then it becomes more positive. So as we move to the right, it becomes a little steep, then more steep, which means it's getting further away from the x-axis. In fact, this looks like a fairly reasonable shape, becoming more positive and more positive. Where do I think the change in curvature occurs? It's kind of hard to tell. And to be honest with you, at this point, since we're doing it graphically, we're just going to have to use our best guess. We will later learn a way to find the inflection point algebraically, which will tell us exactly where it is. But for now, we just have to estimate. I estimate it somewhere here around negative 1 again. That would make that a high point on the graph of the derivative because it was increasing and getting steeper and steeper, but then it's got to start leveling back out and getting flatter so that when it reaches the relative maximum, it has a horizontal tangent line, slope 0. So that means it's going to start decreasing again. And it looks to me like, well, I think that relative maximum is around 1.2, 1.3. So it looks to me like it should be crossing a little further to the left, closer to the 1. In order to get that over there, notice that the point at 2 has to dip below the axis. This makes sense because as we move to the right from the point of relative maximum where it's horizontal, slope 0, and we move to the right, it becomes a little bit negative. And then it becomes more negative and more negative. So it's sloped negatively. So it becomes steeper and steeper, and steeper means further away from the x-axis. So in fact, this should be coming down as well. Now I've got another change in concavity somewhere in here because this last little section is clearly curved upwards. So I'm going to have to stand back and kind of look at the picture and go, well, I'm going to guess somewhere between 3 and 4. I don't know why, but just kind of looks there. But I can also see that you might say it's somewhere between 3 and 5. So somewhere in that range, it changes curvature again. I'm going to put mine a little between 3 and 4, but closer to the 4. What does that mean? That means that I have a low spot down here somewhere, but then it starts coming back up. So I've got a low spot, and then it's going to come back up. Now, as it approaches this change in curvature, what's happening to the graph is it reached the inflection point where it has maximum steepness, and then it starts leveling out again and becoming less steep. As it approaches here, it looks to me like it's coming back towards a horizontal tangent line. We just don't have the rest of the graph to confirm that this is, in fact, a relative minimum. But it looks almost horizontal there. So I'm going to go ahead and make the leap and assume that it is. That means at 6, we have another x-intercept. So how can I draw this so that it looks like there is a relative minimum somewhere in there? Something like that. Hard to say exactly what it looks like, but this looks close to me. Again, I'm not trying to get the graph of the exact derivative function. I'm trying to get the general shape of the graph of the derivative function. Let's check our accuracy and see how well I did. 83%. That may be a personal best. I almost never get above 73. So when I'm looking at this is very close to the graph of the true derivative. Let's put the true derivative on here and see where we differ and how we differ. When we're looking at it, the basic difference is that there is another change in curvature here that I missed. Now, how do you know there's a change in curvature? Because it looks like the graph of the derivative is going to have a relative minimum here. And a relative minimum or maximum on the derivative corresponds to a change in curvature on the original function. But I missed it because I didn't have the rest of the picture. If I'd had the rest of the picture, I probably wouldn't have missed it. Then it comes uphill. It doesn't go quite as high as I drew it, but it looks relatively close to the graph. I've done an outstanding job of getting the graph of the derivative to look very close to its true value. This is all we're trying to do right now. Let's now go back to the notes and take a look at the steps to graphing the derivative. What are the things that we're looking for? When we're graphing the derivative from the original function, we want to locate the places where the horizontal function, where the original function has a horizontal tangent line, the places of relative maximum or minimum on the graph. When you have a horizontal tangent line, that corresponds to an x-intercept on the graph of the derivative. Starting at the far left side and moving towards the right side of the graph, we want to determine, is the function increasing positively sloped tangent lines above the x-axis or decreasing negatively sloped tangent lines that would be below the x-axis. You want to go from the far left to the first x-intercept. So from the far left to the location of the first relative maximum or minimum on the original function. If it's increasing, draw that derivative function above the x-axis. If it's decreasing, draw the derivative function below the x-axis. The steeper the slope, the further from the x-axis. The flatter the slope, the closer to the x-axis. The next thing that we want to do is look at a tangent line at a point that's approaching horizontal, but is not horizontal yet, very flat. Remember, draw the derivative close to the x-axis. It is nearing the x-intercept. If the graph of the original function approaches a vertical line at a point, then the derivative is approaching a vertical asymptote. We saw this on our very first example, the function the square root of x. As the square root of x came towards the origin, approaching from the right, as it came towards the origin, the tangent line gradually got steeper and then it really got steep, approaching a vertical line. When the tangent line goes vertical, the graph of the derivative approaches a vertical asymptote. What if there's a true linear line segment in the graph of the function? Now, we've not had one of these yet. We have not seen an example that has an absolutely straight line section of the graph. But if we do, remember that because it's a straight line section, the slope is constant on that linear segment. If it's constant, then the graph of the derivative function will have a constant value over that interval. It won't be on the x-axis unless the slope is 0. If it has a linear segment where the slope is 2, then we'll have a segment on the graph of the derivative where the y value stays 2. In other words, it'll correspond to a horizontal segment on the graph of the derivative. Let's talk about corners and cusps, our next issue. We haven't seen one of these yet either, but we're going to see one coming up very shortly. If there's a sharp corner, like a V shape, not a U, but an actual V, where there's a corner, there's no unique tangent line at the corner. If there's no unique tangent line, then the derivative does not exist. The same thing happens at a cusp. When you think about a heart shape, that point up here where it comes down and makes a sharp cusp-like shape does not have a unique tangent line. And because it doesn't have a unique tangent line, the derivative does not exist. In the graph of the derivative then, corners and cusps correspond to holes in the graph of the derivative. The derivative does not exist there. It must be a hole in the graph. Then we want to locate the inflection points. These are the points where the tangent line is the steepest it's going to get. These are the changes in concavity or curvature of the original function. These become relative maximums and relative minimums in the graph of the derivative. Places where the slope of the tangent line stops increasing and starts to level back out, these become relative maximums in the graph of the derivative. Places where instead the slope of the tangent line stops decreasing and begins to level out to 0, these become relative minimums in the graph of the tangent line, or graph of the derivative, which is the graph of the tangent line slope. Then we repeat all of these steps between each pair of x-intercepts. The last thing that we want to do is we want to connect the graph smoothly. We want it to be connected smoothly with smoothly curving sections. And if we have any linear sections, we'll connect those as smoothly as we can to the rest of the graph. Now we want to practice this on some actual examples that are static, not in the applet, but instead just on paper. Let's take a look now at this example, which is the absolute value of x. The original function comes down to a sharp corner here at the origin. That means there's no tangent line, unique tangent line at the origin. So the derivative does not exist. On the graph of the derivative, when x is 0, we'll have a hole in the graph of the derivative. On this part of the graph, the slope is a constant value. Remember what the equation or what the definition for the absolute value of x is. It is x provided that x is non-negative, and it's the opposite of x if x is negative. Now that we can see the definition of the absolute value of x, we can use slope-intercept form of a line, y equals mx plus b, to think about what the slope of these two linear segments must be. Again, this is using slope-intercept form of the line, mx plus b. Our b, the y-intercept, is the origin, 0. And so our slopes must be 1 for this segment and -1 for this segment. So when I'm looking at this half of the graph, the slope is 1 and it's constant. It's 1 at every single point. It doesn't become steeper and it doesn't get flatter. It stays a constant 1 slope along the entire section. The section starts at 0 and continues to the right, but we do not have a derivative at 0. So we're going to locate on our graph the location of 1. We have a hole in the graph of the derivative when x equals 0, since it's a corner. And then we have a horizontal line segment to indicate that the slope of the tangent line is constant, constantly 1 on this part of the original function. What about the left half? When we're looking at the left half, the slope of the line is always a -1. It never gets steeper and it never gets flatter. And because of that, it stays constantly a slope of -1 as it moves from -infinity to 0. So down here, again at x equals 0, we have a hole. And then extending off to the left, the slope of the tangent line, the value of the derivative, is constantly -1. This is the graph of the derivative function of the original function, absolute value of x. You can see that it has a jump in the graph at the corner, the place where the derivative does not exist. It does not connect. These are 2 discontinuous parts to the graph. Let's take a look now at another example. In this example, we have f of x equal to the cube root of x. So this is f of x equal to the cube root. We can analyze the graph starting at the left side and moving to the right side, and notice that it is increasing in value. The slope of the tangent line starts out relatively flat, but positively slanted. That means it's going to be close to the x-axis, but positive above it. So out here, I'm just going to guess at where it would be, close to the x-axis, but above it. And then as it approaches x equals 0, where the origin is, it does increase a little bit, but not a lot. It's going up, but very slightly until it reaches -1. So it's increasing, but really not much. However, when it gets closer to -1, it has taken a definite upward slant. So I can assume that at -1, it did take off a little bit more than it has been. It's come up a little bit more. But between -1 and 0, it really changes very rapidly. And we can see this by the change in the curvature of the graph of the original. At -1, it's sloped about like this. But as we approach the origin from the left side, notice how the slope of the tangent line becomes steeper and steeper, always positive, until at the origin, at that one instant, it goes vertical. When the tangent line slope goes vertical, we know the slope of a vertical line is undefined. It does not exist. This corresponds to a vertical asymptote in the slope of the derivative. So we're going to have a vertical asymptote up here when x equals 0. So it looks like our graph is something more or less like that. And unfortunately, my hand's not too steady today, so you'll have to bear with me. If you can draw at least as well as I can, you're doing fantastic, because I am not an artist. Now let's take a look at the right half. Is it still increasing in value? Here at the origin, it's vertical. Notice that as we move just to the right of the origin, it tilts just slightly so that it's no longer a vertical tangent line. It is a positively sloped tangent line, but very high in value, extremely steep. That means a very high slope for the tangent line. That means very high and very far away from the x-axis. So way up here. Then between 0 and 1, it really flattens out a lot and becomes a slope that's less than a slope of 1. Remember, a slope of 1 is a 45-degree angle. So anything that's less than 1 is a fractional slope. So it looks like it changes very rapidly between 0 and 1. So it drops very quickly. And down here, it might have some value like this. Again, we have a vertical asymptote when x equals 0, because at that one instant, the tangent line is vertical and the slope of a vertical line is undefined. That corresponds to a vertical asymptote in the graph of the derivative. Now we want to keep moving off to the right. When we're at 1, it is sloped uphill. And as we go further and further out, it does decrease, but very, very slowly. So we do have this decrease in the graph of the derivative, but a very slow one. So it more or less is a mirror image of what's happening on the left side. This is an approximate graph of what the graph of the derivative function for the cube root of x must look like. Is it exact? No. I'm not trying to get exact. If I wanted exact, I would be using some kind of online graphing utility like Desmos. Instead, what I want is an approximation of the graph, something that I can draw by hand using the information of where it's increasing above the x-axis, decreasing below the x-axis, relative maximum, that would be a horizontal tangent line of 0, so an x-intercept, relative minimum, another x-intercept, and changes in concavity, inflection points. Those correspond to relative maximums and relative minimums in the graph of the derivative. Let's look at another example. This is example 6, which is somewhat similar to the one that we saw on our applet. It has two relative maximums here, somewhere between -2 and -1, and between 1 and 2. It also has a relative minimum right here at the origin. So that means we have 3 x-intercepts. The first thing we can do is go ahead and graph directly below those maximum and minimums x-intercepts onto the x-axis. Now we can analyze the curvature and the increasing and decreasing behavior. Notice that as I move from the left towards the right, as I'm approaching this first x-intercept, the tangent line is very steep and positive. It's sloped uphill and positive, which means that it's got to be very high and positive. But then it has to be decreasing because at the relative maximum, the tangent line is horizontal. So the slope of it is 0. So it's got to be decreasing rapidly to get to here. So it's got to be coming down something like this. Again, on this somewhat parabolic shape, the graph of the derivative is somewhat linear. Now, what happens next? Between these two x-intercepts, I have a change in curvature. It's curved down like a frown, and now it's cupped up like a cup. So where is it? Well, you kind of have to stand back from the graph and use your best judgment. Later, we'll learn algebraically how to pinpoint the exact location. For now, I think it's about there. What I typically do is I'll put an X on the graph where I think the changes in curvature occur. Then I know that above or below those points, I should have a relative max or a relative min on a graph of the derivative. What happens to the graph of the derivative to the right of our relative maximum? Well, it tilts a little negative and then more negative. So it becomes off the horizontal, tilting slightly negative, a little below the x-axis, then more negative, more negative, more negative. It reaches a maximum negativeness at the inflection point, the change in concavity. And then it starts coming back shallow again, flattening out until it reaches the relative minimum. So I'm going to have my graph below the x-axis and going lower and lower until it's directly under the inflection point. and then coming back up towards this. And that should really be more rounded. So let me try to get it more rounded like that. All right. Again, below the inflection point, we have a relative minimum in our graph. It was negatively sloped and becoming more negative, and then it begins to shallow out and approach the x-axis again. What happens now on the right side of the relative minimum? It goes a little bit positive, which means above the x-axis, then more steep, so further away from the x-axis, but still positive, until it reaches the inflection point. So again, it's coming up, until it gets above the inflection point. And then what happens? Well, it reaches above the inflection point, a maximum steepness, and then it's got to start shallowing out again so that it can reach a horizontal tangent line when it gets here to this relative max, which means it has to turn above the inflection point and come back down to hit the x-axis directly below the relative maximum. So it's going to turn and come back down until it hits here. Now what happens? On the right side of the relative maximum, it goes a little negative, then more negative, and it's very quick to increase quite steeply, but always in the negative direction. That means below the x-axis and getting further and further away quite steeply. Notice that the original has 3 turning points, which means it's probably a 4th degree polynomial. Notice that the graph of the derivative has 2 turning points, which means it's probably a 3rd degree polynomial. Notice that it's decreased by 1 when we did the derivative. Later in the semester, we'll discuss the derivative rules, and you'll see exactly why this is so. This is always going to be so. When you change and you look at the graph of the derivative, the degree decreases by 1. Let's take a look at another example now. This would be example number 8. In example 8, we have a really complicated, very difficult looking graph, and we want to see what it looks like. When we're looking at this graph, we've got discontinuity, we've got a jump here, we have a displaced point here, we have an infinite asymptote on the left side and a hole on the right side, and we've got this definite corner right here. We have some weird things going on, but we're going to use the same steps that we've been using to try to draw the graph of the derivative function. We're going to start on the left and we're going to move towards the right. Starting on the left, notice that this section looks like it's cupped up, but the very tail end of it has just a slight bend this way. Well, that's concave down. And that tells me that somewhere in here it changes curvature. So I'm going to kind of eyeball it and guess that it changes curvature about there. Okay, so how does it start out? Well, it starts out horizontal. Horizontal means slope of 0. That's an x-intercept on the graph of the derivative. So we'll put an x-intercept there. Then it goes slightly positive, so a little above the axis. And then it goes more positive, more positive, more positive until it reaches a maximum steepness there above the inflection point. And then what happens? Well, it starts leveling back off again, but it doesn't level off very much. So it definitely turns there and comes down, but it doesn't do much until it reaches this point. Now, how do we handle this jump in the graph? Well, we have a jump in the graph, which means while it's continuous from the left, there's no place on the right. And that means we don't have a unique tangent line. So since we have no unique tangent line there, then we have no derivative there. If we have a derivative, it has to be continuous. And that's definitely a point of discontinuity. Jumps are always discontinuous points. So we have no derivative at jumps. So we're going to have a hole in the graph corresponding to that spot. Now we want to look at the next section, which starts from 1 and proceeds towards 0, or rather from -1 towards 0. When I look at this one, it's not starting out horizontal. This one started out horizontal, but this one starts out already at an angle. That means it starts above the x-axis. It's already positively slanted. So I'm going to just pick a value. I have no idea what it is, but I'm guessing it's around 1. But because that's at the jump, and those two holes should be directly above one another, because it's at the jump point, the unique tangent line doesn't exist, so I don't have a derivative. And then it increases in value more. Wow, it's really becoming vertical. And because it becomes vertical, then I know that I have a vertical asymptote in the graph of the derivative. So the graph of the derivative is going to increase, and approach the y-axis as a vertical asymptote. Now we want to look at the next section. We again have a break in continuity, which means the derivative cannot exist. So the derivative does not exist here at x equals 0 because we have a break in continuity. We have a hole from the right side and an infinite asymptote from the left side. When we're looking, however, at the next section, which extends between 0 and 1, we can see that this section is actually definitely a linear segment. It's a straight line. It's not curving at all. There's no curvature to it. It's not cupped up. It's not cupped down. It is a line, absolutely straight. If I look at this section right here, I can estimate what the slope of it is by looking to see what the vertical change is with respect to the horizontal change. That's rise over run. So it looks like it drops 2 and then moves 1 to the right. That's a slope of -2. But again, I have no derivative at x equals 0. I can't have a derivative at 1 either because I have a displaced point here. I have a break in continuity. There's no unique tangent line. So on this section, I'm going to have a hole at x equals 0, and I have a horizontal line segment that extends out, indicating that the slope of the tangent line on this section is a constant value, and it's always constantly -2. Now I want to look at the next part, which is this part here. It is also a linear segment, so it's going to have a constant slope. If I'm looking at this section, it looks like I have a change of 2.5 over a horizontal change of 1. So I think my slope is about 2.5. Now, again, at 1, I cannot have an actual derivative because I have a displaced point. So I'm going to have a hole there, and then it extends to the right over here towards 2. Now, what happens at x equal 2? At x equal 2, I have a sharp corner. Anywhere that we have a sharp corner, we do not have a unique tangent line. If we don't have a unique tangent line, then we don't have a derivative. That will correspond to a hole in the graph. So we're going to have a hole here on this segment at x equal 2. What about this last segment? It's also a straight line segment. It's kind of hard to judge the change in the slope, but it looks almost parallel to this one, which we said had a slope of -2. So I'm guessing it's about -2 again. So between 2 and 3, it looks like the slope is constantly -2. So I come down here below 2 where the tangent line does not exist, and I draw a horizontal section. And this may continue out that way further, but we don't know. There's no arrows, so we don't know if the graph continues or just stops. Is this exactly what the graph of the derivative looks like? Probably not. Is it close to the graph of the derivative? Yes. Does it have the basic shape of the graph of the derivative? Yes. Does it tell us something about the derivative? It tells us a lot. We can see where the derivative is increasing, where it's decreasing, and where it's constant. We can tell where the derivative has a relative maximum. We can see where the derivative increases without bound and approaches a vertical asymptote. Let's take a look now at one more example, example number 9. This is an interesting function. It has several changes in curvature, but it also has something that's called a saddle point. If you do much hiking in the mountains, you know what a saddle point is. It's like a false summit. It looks as you're hiking like you're reaching the top of the mountain. And when you come up over the crest, you realize instead that it's a flat section and then it goes up again. You just couldn't see the second rise. So it's like a false summit when hiking. This point right here is called a saddle point, like saddles, riding horses. So what is a saddle point? Well, it's a place where the slope of the tangent line goes horizontal, but then continues in the same pattern. So for example, from the left to the right, this is very negative, very steeply sloped, very steep, and then it begins to shallow out. And at this one instant on the saddle point, it goes horizontal. So the graph of the derivative starts out very negative, very negative, very negative. And at that one point on the saddle point, it goes horizontal, right? But then what happens? So it was negative, 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 less negative, approaching 0, 0. Then it tilts. It doesn't go positive, it goes back negative again. So it was decreasing, goes to 0, and then it's decreasing again. This is a saddle point is a place where it goes horizontal for one instant, but then it continues with the same decreasing behavior, or increasing horizontal for a moment, then increasing again. So on this section, it's a little negative, more negative, more negative, more negative. Uh-oh, what's going to happen? We have to have a change in curvature. You can see here that this part is cupped up and this part is cupped down. So we have a change in concavity here. And we also have a change in concavity here where it's cupped down and then it's cupped up. All right. So when we're looking at this section, what do you think we should do for the next part of the graph? What do you think it would look like when we draw it? As we come off of that horizontal, it goes a little below the x-axis, then more below, more below, more below. We need to find that change in concavity where it goes from concave up to concave down. Gosh, it's hard on this one. Really hard. I'm going to guess somewhere here around 2. So this means it came up, curved, went down, became more negative, more negative, more negative until it reached a relative minimum under that inflection point. Then what does it have to do? Well, it's got to become less negative and get closer to the x-axis, because at the relative minimum, it's on the x-axis, it's an x-intercept. The slope of the tangent line is 0. So it's directly above the relative minimum at x equals 3, we should have an x-intercept. So it comes back up like this. Now what do we have on the last part? Extending to the right, it goes a little positive, then really rapidly increases to become very positive. That means it starts out low, but rapidly increases like this. Again, this is an approximation of what the graph of the derivative function looks like. I don't really know exactly how low it goes. I don't really know exactly where this inflection point is. We will later use algebra and some calculus techniques to find the location of both exactly where the inflection point is and precisely how low it goes. All right? I hope this helps you to draw the graph of the derivative function based on the original function. In the next video, we'll start with the differentiation rules, which starts with the algebraic approach to the derivative. So we've covered the definition and we've covered the graphical. Now we're going to cover the more algebraic based rules for the derivatives.